We are about to undergo the fourth industrial revolution. Historically speaking, industrial revolutions have been caused by the arrival of general-purpose technologies, or GPTs. For example, the first industrial revolution was triggered by the invention of steam engines, which could be utilized for various uses, such as weaving cloths, moving trains, and sailing ships. The upcoming revolution is driven by the development of artificial intelligence. Generative AI, particularly large language models, are dramatically transforming how we work and live. Though it's quite certain that things are changing fast, it is impossible to predict the future. In the face of volatile situations, what we need to do is not to predict the future, but to return to basics and understand the fundamental principles. The specifics are constantly changing, but if you grasp the essence, it will be a reliable foundation to make better decisions. Now that intelligence is no longer a human monopoly, we need to know what intelligence actually is, and understand the potential of AI, in comparison with the human brain. What are the similarities and differences between human intelligence and machine intelligence? Contrary to the general impression, AI is not a perfect and universal solution. In fact, machines cannot perform well, without enough and proper learning, like humans. For example, Mark Twain was one of the greatest writers in American literature, but obviously he couldn't even speak a word when he was a newborn baby. He needed to absorb vocabulary and learn grammatical rules, by being exposed to English spoken by people around him, listening to his mother read aloud, and having his mistakes corrected by his teacher. He might have said, "I go to the park," and his mother might have corrected him by saying, "You went to the park, right?" Similarly, machines cannot generate sentences without sufficient learning. For example, large language models learn vast amounts of text data from various sources, papers, literatures, news articles, descriptions in encyclopedias, and so on. The data size is equivalent to 10 million books. From this massive dataset, the algorithm extracts correct sentence patterns. Also, it creates fill-in-the-blank questions for self-learning to improve the precision. The same is true for image recognition algorithms. For a machine to identify a certain object in a picture, it has to learn from tens of thousands of image data. As of 2024 at least, AI can only function well when it has properly learned from huge amount of data. By contrast, a human child doesn't have to read 1,000,000 books to speak a language, or train on thousands of pictures of apples to identify the fruit. Some people have the unrealistic expectation that AI can easily solve everything, but to build and fine-tune AI, we have to prepare an enormous volume of data and get machines to efficiently learn from it. Surprisingly, human intelligence and artificial intelligence process information in similar ways with similar structures. The majority of our cognitive functions are handled by a part of the brain called the neocortex, and each unit of this region is composed of 6 layers. Lower layers receive specific and fragmented information, and as information moves to the higher layers, the process becomes more integrative and abstract. Think about the case when you hear someone say, "song." First of all, the lowest layer of our neocortex column identifies each phoneme captured by the auditory system, namely, your brain recognizes the sounds of S, O, N, and G. Then, these information are sent to the higher layer where they are combined and perceived as a word, song. Going further upwards, the recognized word is integrated with the entire sentence and the context. If you heard words like band or the Beatles right before, the higher layers of your neocortex will conclude that the word song means what humans sing, not a bird's cry. This is how your brain makes sense of the word song in verbal communication. Artificial intelligence possesses a similar hierarchical structure. In natural language processing, the lowest layer identifies specific individual characters or words. As it moves towards the upper layers, the processing becomes more comprehensive and abstract, integrating co-occurring words, the underlying context, and so on. Why are they so similar to each other? It is because the foundation of the latest machine learning technologies were inspired by the structure and functions of the human brain. In a sense, the development of computer science is the result of our challenges to reproduce human brain functions, with silicon and mathematics. Computers have 4 distinctive abilities that humans can never have: variety of perception, connectivity, replicability, and updatability. First, machines can perceive information that humans cannot. For example, a human driver can only rely on visible light within the range of infrared and ultraviolet to understand the surroundings. However, a self-driving car detects a wide variety of information, such as laser light and supersonic waves, when it's equipped with necessary devices. Second, computers can be connected to each other. Since humans are separate individuals, human drivers cannot communicate to each other instantaneously. When 2 vehicles are about to collide, the drivers cannot avoid it by telling each other to turn right. Unlike human drivers, self-driving algorithms are not separate entities. They are part of a single network connected on the internet, so they can communicate to each other to drive safely, smoothly, and efficiently. Even if you are the best driver in the world, you will fall far short of self-driving algorithms for a single reason: that you are not connected with other vehicles. Thirdly, machines can be replicated. Imagine how much it would cost to produce one capable doctor. He or she takes more than 20 years to mature, and has to finish the whole expensive course at a medical school. Despite such a huge cost, the doctor has to retire after 40 to 50 years. Therefore, society has to spend the cost of producing a capable doctor all over again. By contrast, machines and algorithms can be replicated instantly and inexpensively. It may take years and billions of dollars to train an algorithm for medical diagnosis, but once the final product is achieved, it can be mass-produced and deployed at hospitals all over the world. Furthermore, every time a new medical paper is published, these algorithms can easily be updated simultaneously, while human doctors are too busy working, playing with their children, and doing the housework to read all these papers. In the face of such substantial differences in performance, where will there be room left for human workers? One of the most profound differences between human and computer intelligence is whether they understand meanings. If you ask machines to translate a word apple or identify apples within a picture, they will do the job perfectly for you. However, computers don't understand what an apple actually is. We humans hear the word apple and immediately remember how it tastes and feels in our mouths, or possibly associate it with a certain technology company or a legendary hero of Switzerland. Computers never act this way, but, up till now, this doesn't seem to matter. Alan Turing, the great mathematician who laid the foundations of modern computer science, already had insight into this matter back in 1950. He proposed the idea called the Turing test. When you talk with a machine in a natural language, if you feel that you are talking to a real person, the machine has intelligence. In other words, he shifted the matter of whether the machine has intelligence or not, onto the matter of subjective perceptions of human beings. The Turing test seems right. For example, large language models don't understand the meaning of the text they generate. They are simply sequencing words that are statistically most likely to follow the previous word in the given context. Whether you ask for career counseling or tutoring in quantum physics, ChatGPT and Google Gemini will give you better answers than the vast majority of the human population. However, they are merely pretending to understand, and never know the dilemma in difficult career decisions, and mysterious behavior of quanta. Yet, they are capable enough for commercial use. In conclusion, it makes little sense to consider which intelligence is better than the other. The CEO of NVIDIA, Jensen Huang, said, "Some worry that AI may take their jobs. Someone who is an expert with AI will." What truly makes sense is to utilize computer intelligence to effectively complement human intelligence, which requires a profound understanding of the features and differences of these two types of intelligence.